Good morning, everyone. My name is Jakub Wręczycki, and I am PhD student at Lodz University of Technology. And in general, I am working on synthesis and development of sulfur organic copolymers for various materials engineering applications. But recently, I've started wondering what will happen if we use sulfur organic copolymers as curing agents for rubber. And this is the topic of my today's presentation and the topic I'm currently working on. So it is well known that sulfur occurs in nature in native form or in form of various sulfur-containing minerals. But we have to keep in mind that sulfur is also a byproduct from petroleum industry, mainly from hydrodesulfonization process. And enormous amounts of sulfur are produced annually as a waste. So it is necessary to utilize them, and one of the very promising approach, which is connected with thermal behavior of sulfur, is to transfer them into chemically stable polymeric materials. The most thermodynamically stable form of sulfur is orthorhombic sulfur. During heating, it converts firstly to monoclinic sulfur, and then at temperature of approximately 119 Celsius degree, the crystals of monoclinic sulfur and orthorhombic sulfur melt into yellow low viscous liquid, and further heating leads to ring opening polymerization and resulting in creation of polymeric sulfur diradical species, which polymerize together into polymeric sulfur, described as SW. But when we now quickly quench the polymerization mixture, we obtain something like plastic sulfur, which is a mixture of polymeric sulfur and sulfur in form of 8-member rings. But polymeric sulfur is unstable and quickly recombines at ambient temperature to monomeric form, so its stabilization is crucial to obtain any useful product. And we can stabilize polymeric sulfur during polymerization process by copolymerization of sulfur with unsaturated organic species like, for example, styrene, dicyclopentadiene, turpentine, on limonene, because the thermally generated d radicals during heating sulfur are very reactive with unsaturated bonds. And in my research, I used a classic glass four-neck reactor, which was equipped with condenser, mechanical stirrer, thermometer with thermocouple to synthesize sulfur organic copolymers. I synthesized one polymeric sulfur and 8 various sulfur organic copolymers, 3 of them based only on sulfur and dicyclopentadiene, but 5 of them based also on another comonomer, which was turpentine, styrene, limonene, furfural, and LP23. And LP23 is a liquid thiocol rubber. During copolymerization, I tried to keep up similar conditions. So the reaction temperature was 140 Celsius degree, and the reaction time was 3 hours. But in case of sample 3 and 4, I used another approach, because I firstly heated sulfur to 160 Celsius degree to make sure that all the rings are open, and polymerize it for 1 hour. And then I decreased the temperature to 140, and I dropped the dicyclopentadiene and copolymerized it for 3 hours and for 6 hours. As I said at the very beginning, the copolymerization product is a mixture of unreacted sulfur, otherwise soluble, and polymeric sulfur, otherwise insoluble. To purify it and indicate how the mass ratio of unreacted and polymeric sulfur contents, I indicated it according to ASTM norm. And in this experiment, toluene was used as solvent of elemental sulfur. And looking at the results, the highest polymeric sulfur contents exhibit copolymer with styrene, then with limonene and turpentine. And the average sulfur content in all copolymers is approximately 30 to 35%. And when it comes to the polymeric sulfur, as I said, is unstable, so the contents of macromolecules are very low, and more than 90% are unreacted sulfur in form of orthorhombic. So polymeric sulfur may behave during vulcanization process as classic orthorhombic sulfur. When it comes to the DSC, I use this method to track the purification process of sulfur organic copolymers, because as you can see on the thermograms at the left side, some peaks originating from crystalline phase of unreacted sulfur exist, and after purification the peaks totally disappeared, so the purification process was successfully performed. When it comes to the composition of rubber mixes, I use SBR rubber as a matrix, also stearic acid, zinc oxide, CBS as an accelerator, and sulfur and sulfur organic copolymers as curing agents. All the mixes were prepared in an internal laboratory micromixer, and the total mixing time was 10 minutes. But when it comes to the sulfur and sulfur organic copolymers content, I have to use some excess of sulfur organic copolymers because I wanted to keep up the same sulfur level in all rubber mixes. So when it comes to the crosslink density and structural analysis, I carried out equilibrium swelling of vulcanizate, and then I calculated the crosslink density from Flory-Renner equation, and I also performed thioamine analysis to indicate how many polysulfide, disulfide, monosulfide, and carbon-carbon crosslinks participates in rubber structure. So looking at the results, we can gather that sulfur organic copolymers before and after purification are taking part in curing process, and in some cases lead to obtain vulcanizates with higher crosslink density than the reference sample, which was cured with orthorhombic sulfur. But when we look at the results of thioamine analysis, we can see that the participation of various crosslinks evolve proportionately to increasing or decreasing crosslink density. However, we can see that what is a little bit interesting, after samples cured with copolymers after purification contains less polysulfide crosslinks and simultaneously more disulfide, monosulfide, and carbon-carbon crosslinks than the reference sample, and it can be a little bit surprising at the first glance. When it comes to the mechanical properties of vulcanizates under static conditions, namely elongation at break, we can see that the samples cured with sulfur organic copolymers exhibit classical dependence between crosslink density and their elasticity, because samples with lower crosslink density exhibit higher elongation at break, and the other way around. When it comes to the values of modulus 100%, we are not observing very significant changes in stiffness of materials, also the classical dependence. But what is very interesting is the results of tensile strength, because the samples cured with copolymers after purification exhibit significantly higher tensile strength than before purification, and significantly higher tensile strength than the reference sample. And I think that it can be explained by the fact that the long macromolecules of sulfur organic copolymers may join the rubber macromolecules and make it more stiff. Or, for example, the curing process may flash without any modification of macromolecules of rubber, and, for example, like cyclic sulfide structures, and we observe it as increase of tensile strength. So, coming to the end, what about next steps? Firstly, I'd like to develop the freezing point depression method, or otherwise cryoscopic method, in crosslink structural analysis, because I performed some initial experiments of selected samples, and I noticed some positive trend, because when crosslink density calculated from Fourier-Renner equation increases, then the delta T also increases, and the delta T is the difference between cyclohexane crystallization temperature, which was introduced to the crucible, or to the DSC crucible during analysis, and the cyclohexane temperature, crystallization temperature, which was trapped between the crosslinks in rubber structure. So I think the trend is very positive, because when we have higher crosslink density, the crosslinks are located near each other. So, the solvent are not able to crystallize, and it takes long time to crystallize. So the temperature is moving to the lower values. So the delta T is higher. I'd also like to perform a crosslink density analysis by equilibrium modulus and then calculate it from Munir-Rivlin model. I'd like to finalize DMA analysis of prepared vulcanizates, perform Raman spectroscopy of sulfur organic copolymers, because it can give valuable information about structure of copolymers. And I also like to prepare styrene butadiene rubber-based mixes with carbon black, and then studying the mixes and their vulcanizates and compare it to obtained trends in recent studies. So to sum up, utilization of sulfur organic copolymers as curing agents for rubber enable effective cross-linking process. And in curing process participates not only unreacted sulfur, which is present in product of copolymerization, but also polysulfide macromolecules, and it was confirmed by the cross-linking after purification. In general, vulcanizates cured with sulfur organic copolymers after purification exhibit more interesting mechanical properties than before purification. And developed procedure based on DSC provides simple and effective way to track purification process of sulfur organic copolymers. And the last one, freezing point depression, seems to be a very promising method which may give valuable information about rubber structure. And thank you for your kind attention.